please confirm if you can hear me?
Yes, we can hear you.
Okay, thank you very much. All right, so we're going to continue with cutting edge AI application. And yesterday we ended just before autonomous driving. All right, so all right, so we talk about intelligent driving. So when we talk about intelligent driving, we just referring to autonomous driving or smart driving. So those are the terms used when we're talking about self-driving cars. So we can talk about intelligent driving, autonomous driving, or smart driving. Okay, so these refer just to cars or vehicles that can perceive the environment and make decisions to navigate the roads, to avoid human and avoid every impact or everything and respect the rules of the road. So the technologies behind these cars are what we will refer as intelligent driving. So this will basically combine all the sensors, all the control systems that you're going to have that are powered by AI. Okay, in order for the car to be able to understand the environment, which is the road, or in your yard or anyway, for the car to drive by itself. You understand? So, and that's happening in real time. So all these sensors have to work in real time. Okay, so we will basically, when we look at this the history of these technologies since the 1995 that researchers started already there. So you have, for example, in 1995 already a Mercedes was able to implement a system that could detect the speed, the maximum speed, in order for the car not to exceed the maximum speed in the freeway. So as time goes, technologies are really advancing, and today we have cars that can actually drive by themselves. Some cars can only park, like parking. They can do a self parking, but we are already on the level where we have cars that can fully be automated. Cars that can drive by themselves from your house to your workplace on a freeway or in any other type of environment. Okay, so when we're looking at how these self-driving cars are really lifting society up, we have with this intelligence driving in places where they are really using them, they've noticed that there have been a reduction of road accidents, because a lot of road accidents are caused by negligence. Human being distracted, someone looking on their phone or using their phone while driving. You have drunk drivers. You have people rushing because they have to be somewhere. So it's always somehow related to some human error that we end up in many accidents. So now with self-driving cars, we avoid a lot of accidents, right? There will be accidents, of course, but we avoid a lot of accidents because decisions are taken by the computers. Okay, so about 1.2 million people died from traffic accidents every year. You understand? So when we're looking at this, we realize that we can solve this issue because 90% of these traffic accidents are caused by human error. Okay, So, and then another advantage with this is that it's really convenient and efficient to travel. So, these cars, this intelligent driving can allow people to just relax as you're driving, you're moving from one point to another point. You can travel long distances. Sometimes when you're driving yourself, if you're traveling from Johannesburg to Cape Town, you will have to stop and rest, or just because you're tired and things like that. But with autonomous driving, the car can just drive while you're relaxing. Okay, so those are some of the advantages of this technology. So if we have to compare manual driving and intelligent driving, so when we find ourselves in situation where let's say the car wants to know where it is, right? Where am I? So as human, we have to look. We have that challenge in terms of if you get lost somewhere and you don't know the location, you get stuck now. But with an autonomous car, this car can easily connect to the GPS itself and actually locate itself and know where exactly the car is, right? So you need to remember, because for us, we just dealing with, even when we're navigating the map and everything, we're just dealing with our eyes and our ears, and we think, and then we can use our hand and our feet. But the car is able to sense and position itself, right, before it makes decisions. So it can sense where it is, the location of the car, and easily work with that. So in terms of the perception, in terms of sensing, for the car to be able uh, to get somewhere. So if we want to get somewhere, we have to use all the cameras, the radars, the central control units, and then the car would automatically use the steering wheel and the pedals in case for the car to move. So the car is able to sense the environment by using the cameras, right? So it senses the environment by using the camera. So the cameras will detect the traffic signs to know which lane the car is in, to detect the pedestrians, right? Because you can't just detect the pedestrian with the sensor, because if the sensor is detecting the pedestrian, then that means that uh, the car will be stopping every time, even if there's a moving car in front, and it's just going to be alert. But you have the cameras that has to identify what object is in front, right? And identify that if it's human being, you have to automatically stop, you know. They need to, the cameras needs to look at all the traffic signs and interpret them and understand what that traffic sign means. So if we have a sign that's the stop sign, the car needs to identify that sign through the camera and be able to stop, right? So, and then we have all the radars. So the radars that we have will detect different obstacles, measure the speed. So basically, if there's a car in front, it can detect that car in front and measure at which speed that car is going, and measure at what speed you are going, and know when to slow down so that you don't reach where that other car is, right? So you have all those devices in order for you to detect that. So basically, the AI algorithm behind that will process all the sensor data to identify the objects, the lanes, the traffic lights, and other objects on the road, right? And then it's going to make the decision. So the decision making, when we're talking about the decision making of the car, so the decision making is basically to determine how the car should act based on the perceived data. So based on the data that the car is getting from the cameras, from the sensors, how should the car behave? Should the car act? Should the car stop, or the car should slow down? You understand? Um, so the decision making will just involve as well the planning, so the path planning, which road to take, which lane to take. So if the car knows that in 200 kilometers it needs to turn left or exit the freeway, so the car will start making a change of lanes before that decision is taken, right? So it needs to do a behavior prediction and risk assessment. So to see if there's cars on the side, it mustn't just change the lane. So the car must look at all those things. Okay, so that's one of the things. And now we have another component, which will be the control. So the control is done by the steering wheel, right, and the pedals. But for human, the control, we're controlling everything with our hand. In terms of our decision making and planning, we just do it with our brain. We think of it, we see what to do, right? But for the what you call this, for the car, it has a central control unit, which works as the brain of the car, right? In terms of sensing and positioning ourselves, we use our ears and eyes, but the car will use the cameras and radars. So this is how we can be able to navigate. Okay, so obviously the car will use the GPS and all the sensors to get the location. Okay, and yeah, so there's many levels of autonomous cars. As I said, you have other cars like we have like levels. You have other cars like the normal cars that we have on a daily basis. Those cars are classified as by the Society of Automotive Engineers. Those cars are classified as a level 0 car. Why? Because everything is done by humans. So the human driver will do everything. And then you will have like a level 1 will be a car with like a driver assistance, such as cruise control. So you have cars that you can basically let the car identify a certain speed. So when it's on the freeway, it needs to slow down or it mustn't go above a certain speed. You understand? And then you have another level where you have kind of partial automation, where the car is able to adapt itself to a certain speed. It's able to keep the lane, you understand? So, and then you have another. So you have, in total, you have like 5 levels. So the level 5 will be the full automation, which will basically be where the car drive anywhere without human input. Right. So, is there anyone in the class that's will not go into a self-driving car? Like if you have to request a taxi and then it's a self-driving car, like the taxi, like a self-driving Uber. Anyone would think they wouldn't go in? Is there anyone who does who think that anyone who think that they wouldn't be comfortable in the car without a driver? So if I understand, everyone will be fine with that. All right, so you can see, guys, you can see how a lot of jobs will be lost because these self-driving cars, where we're going is that we're going to have the smart trucks and delivery vehicles. So basically, you don't need someone to do a delivery, that's the thing. You have autonomous buses and shuttle, so you can actually request, and then all the taxi. It's gonna be a problem. It's gonna be a problem because you're gonna get to places where taxis do not need drivers, and people will trust more taxis without drivers, also for safety issues. You know. Okay, so the benefits of this obviously will be to so basically we're reducing the roads like increasing the road safety by reducing human errors. So the more self-driving cars we have on our roads, the safer the road will be. Okay, so this will also help in terms of improving the traffic efficiency and reduce congestions, because remember, sometimes we have traffic on the road because some people are not respecting the robot on a certain road. Now, when they're not respecting the robot, now they end up being late to pass by the point. And then when the robot is green on the other side, the other people cannot pass. And then all that creates the traffic. So we can avoid that because self-driving cars will respect the road rules. Okay. So another advantage would be maybe people who do not know how to drive will be able to have cars. Because if you don't know how to drive, it's fine. The car will drive itself. Okay, and we can also talk about reducing the fuel consumption, because if the car is driving by itself, a self-driving car will actually know exactly how to drive properly in order to use your petrol properly, you know, compared to human, because you accelerate where you're not supposed to accelerate that much and all those things. So that's those are some of the issues. But guys, what do you think will be the challenge? What can be a challenge for a self-driving car? Like implementing this in our society. What do you think? What do you guys think can be the challenge, the biggest challenge? Some of the challenges. What do you guys think can be the challenge? Mm,
I think it would be the data they are trained on.
okay, yeah, yeah, that can also be, uh, yeah, the data they are trained on. Anything else? Anybody thinking of anything else that can be the challenge?
Hello.
Yes, what can be the challenge?
About technical limitations.
Sorry, I didn't hear you.
Limitations. Like
Yeah.
self-driving cars struggle with complex scenarios like construction zones, inclement weather, or unexpected pedestrian behavior, and like that.
Yes, yes, yes. That's right. Because the weather condition can affect the sensors. You know, when there's like fog, there's rain, snow, all those things can affect the sensors, because the sensors can be blocked by the snow, for example, and now the car cannot sense things properly. Yes, you are right. So the weather condition can be a problem. Anybody else think of something else? How about unpredictable traffic scenarios? See, you have, you think of how you have, for example, in South Africa, how taxi drivers drive, you know, moving from one lane to another lane, all those things. How does a self-driving car quickly react to that? You see, so those may be challenges, because so far these cars have been tested in countries where people really respect the traffic. You see, you have, for example, in China. In China, your behavior on the road is affecting your credit score. So people have to drive well, because you don't drive well, it affects your credit score. So people respect themselves on the road. Uh, so when they testing these self-driving cars in those environments, everything looks good. How about in our environment, where you have uh, taxi drivers driving from one lane to another lane without indicating, just passing in front of the car. See, so you have that. And another thing as well another challenge as well, I'm thinking, can also be the security in terms of the data privacy. We have the data privacy. We have the security in terms of cyber security. Imagine a certain company, maybe a taxi company using self-driving cars, and if they can hack that company, you see how they can change the direction of many of the clients. You see, so those are issues that needs to be considered. Okay, all right. So I think we've mentioned these subsystems of intelligent driving already. So in terms of sensing, we need to work on ultrasonic radar, wave radar, cameras, LiDAR. So we have all this. In terms of thinking, we have the sensing, convergence, positioning. The car needs to do a planning, prediction of different move, quick decision making and control. In terms of acting, the driving system, braking system, steering system, drivetrain, security system, and the comfort system. So this is the complete system to create an autonomous car. Now, there's a service that is provided by Huawei called the Huawei MDC. Okay, so Huawei MDC is a computing platform. So it's a platform if you want to create the system that can be installed on self-driving cars, right? You can create those systems with the Huawei MDC. All right. So things are simple now. Things are very easy. So with the Huawei MDC, which MDC actually stands for Mobile Data Center. Okay, so with the Huawei Mobile Data Center, it's sometimes they also call it the Mobile Data Center for Intelligent Driving. So this is just a driving computing platform. So this is for self-driving car. This is designed to basically power the autonomous vehicles and intelligent driving system. So it's the way it works is it's provide high performance in terms of computing capabilities. So we have access to, remember we need cameras, all the radars and everything. And it also even come with a simulator. So basically you can simulate a real environment. As you're training your model, you can actually create roads, but it's not real, but it's a simulation, but your model will learn from it. Okay, so so this platform obviously will be able to really handle massive amount of data from cameras, from radars, and all the sensors. So it can basically support all the real-time AI processing for planning and control. Okay, so this architecture will also help you in terms of building all your neural network. This can help, especially with tasks like objects recognition, lane detection, path planning. So yeah, this is one of the platforms that can be used. Okay, and you need to note that it's actually using a very in terms of hardware. We have powerful CPUs and GPUs for all the AI processing. Okay. This will basically you will really use this, especially when you're processing data from sensors in order to detect different objects and that. Okay. Okay, so So now this cloud platform will help in terms of providing all the data. So you basically look at the data in terms of it looks like it's an environment that you can generate an environment that looks like a real environment, looks like a road with cars and everything. So this can actually help in terms of uh, data storage management, in terms of your training services, all your training start algorithm, managing your model, and then you have a simulation services where you can actually simulate scenarios. Okay, so here you can simulate scenarios such as, like you can create cars passing at high speed or a car breaking the rules of the roads to see how your car is actually going to react to that. So you can have this virtual environment which can actually be used as if it was a real environment. So those are the advantages of using the MDC as a platform, and because everything is done for self-driving cars. Okay, so it's gonna help a lot in terms of reducing the development time and cost. Okay, and just to help you move forward in terms of creating this system. All right. So I think that's all for this. Okay, just let's answer this quiz. Multi-answered question. Whenever they tell you see multiple answer question, it means that the answer can be more than one. Okay. When you see single answer question, then there's only one answer. So please pay attention or be careful in your exam whenever you see this. All right. Which of the following scenarios can okay, we haven't done knowledge graph. Oh, we did knowledge graph. Wait, we did yesterday. We did yesterday. Which of the following scenarios can knowledge graph be used? Okay. Which of the following scenario can knowledge graph be used? We did this way. Sorry?
A and B.
A and B. Okay. Anybody else? Think of something else? Anyone else?
A, B, C.
Yeah. Oh, that's the answer I will also support. So it's A. We have search engines. When you have a search engine, you have, if you're searching about a certain information, the machine has been created with the knowledge of understanding that information and every information that is related to what you're searching for. You have your product search, product keyword search, yes, and the QA, so question answers bot. Because for the question answers bots to give you the answers, it needs to have a certain knowledge about a certain topic structure. So we have A, B, and C. Okay. Second one, in intelligence driving, LiDAR is the only sensing device. True or false?
False.
False. Yeah. Perfect. False. Because when we go to sensing devices, we have all these devices. So there's many sensing devices. All right, guys. Now we're going to talk about something more technical. So we're going to talk about quantum computing and machine learning. So we're gonna start it today and complete it tomorrow. Okay, so Okay, you guys heard about the word quantum physics. You don't need to know what it is, but if you heard that word, is there anyone who has never heard someone mentioning quantum physics? Is there anyone who has never heard the word? Yeah. So when we when we talk about quantum computing, we first looking at what is actually quantum. So when we hear it's also depend uh, on the area, right? But we're going to first talk about it in terms of physics, and then we're going to talk about it in terms of computers, because when we look at in terms of computers, when we're talking about quantum computing, we actually based on the quantum mechanics, the principle of quantum mechanics. So what are those principles? You have what we call, for example, superposition. So when we look at a normal computer use bits. So basically we have zeros. Uh, yeah, so we have this one, this one, right? So in a normal computer, in a normal classical computer, we're going to have zeros and one. So all the bits, everything that we do on a computer are zeros and one, right? So basically, if you even your name or even everything on the screen behind the computer, the way the computer understands the information, it understands it in this binary. So it should be a zero or a one. It can't be both, right? Zero or one. Okay. But in quantum computers, whenever you have a quantum computer, the quantum computer do not use bits, right? That's why they are so powerful. When you hear machine learning, you hear those big computers will tell you, this is a quantum computer, very powerful. It doesn't use bits, it uses qubits. So these are things that we're going to talk about tomorrow. It uses qubits. So the qubits can be, you can have 0, 1, both at once. So you can have 0, 1, or you can have both at once. You have 0 and 1 at the same time. So that's what they call qubits. But when we talk about bits, a bit can only be one thing. It can be a 0 or a 1. Okay, so with quantum computers, the fact that it's used these qubits, that will help because when we talk about the 0 and 1, that's why they say the superposition. So in this case, then these quantum computers will really process massive amount of data in parallel at the same time, right? So which will help us solve many problems, especially when it comes to deep learning, right? Machine learning. So that's one of the things that you need to note about that. Okay, so we if we have to compare now classical physics, right, and quantum physics. When we're talking about physics now, we want to compare classical physics and quantum physics. There's a lot of things that will be different in terms of the energy, how the energy is perceived in normal physics, which is classical physics, and how it's perceived in quantum physics. How's the state of motion in terms of everything that is moving, the properties, you understand? So that's um, that can be so when we're talking about, for example, classical physics. When you talk about classical physics, it can be an example such as you want to predict the motion of planets. Very easy, motion of planets. You want to do something like to calculate the trajectory of a ball. If you a soccer player shoots the ball, you can actually predict the trajectory of the ball, right? So when we're looking at quantum physics now, we talk about things like the behavior of electrons in an atom, for example. Okay, so it's more than that. It's more of the little detail that we have in the whatever in the physics of things. So in terms of energy, if we have to compare in terms of energy, in terms of energy, if we have to compare classical physics to quantum physics, in terms of energy, for classical physics, we say that the physical quantity is considered continuous, and the system energy can be any value. So when we say continuous, it means that it can be any value. So when we say, for example, if a ball is released at any position, at the beginning, okay, and the system energy is smooth and continuous parabola. So basically, if you want to understand that, we're gonna look at something like, let's say you throw a ball upward, right? If you throw a ball, you are here, you throw a ball, it goes upward. This is what the ball is going to do. It's going to go up, and then the speed will go back will reach its maximum. And now you have your gravity that is going to be pulling it down until the ball goes down there. So at each moment, we can actually quantify, at each moment, we can actually measure what was the speed at that moment. You understand? So when we look at that now, we can say the energy value of the ball was continuous. It touched every point. It never stopped. It never stopped anyway. So the energy was continuous. Okay? But which means that at any point we can have what was the amount of the energy. So when we throw the ball upward like that, we can have any speeds depending on how much the force was applied. So when we're talking about the energies, when we talk about kinetic energy, for example, we can see that there's a change of the kinetic energy, and then it creates kind of a parabola there. So that's how the ball will do. Okay, so there will be no restriction on possible energy value. So the energy was the same. Good. But when we talk about quantum physics, think about it like states. Something that will give us maybe a low energy here, and then it reaches a certain point. It goes here, here, here. See, so that's how in quantum physics things work. So in quantum physics, the energy value can only exist at specific levels. So we already have certain levels. Let's say, for example, this is level, what is that? Okay, so if we have to create, maybe this is our energy is being shared. So let's say this is time. This is the energy. So if we throw the ball from here, can you see at each level, there will be a value up to when it arrived there. But here, we're going to have something like this. So we have time, we have energy. So as energy goes in the quantum physics, we're going to stay on one level, and then we move to second level, we move to third level. So basically, the value, the energy value can only exist in a specific level, not continuous. So that's the difference between quantum and classical physics. So an example of this can be how an electron in an atom can only occupy maybe a certain orbital. So when we look in chemistry, we have this, depending on which element you're talking about, these are the orbitals. You have something like this. So here you can have maybe an electron here, an element with one electron on the last, then maybe two. I'm just giving you an example. So which means that an electron can only occupy a certain orbital. You can't have it in the middle. You can't have it at any position. It has to be on that level. So we have on this level, on this level, on this level. So if you have a certain atom that has 4 levels, so we can only have on those 4 levels. It can't be anyway. So it cannot exist between 2 energy levels. Okay. So when the atom like that will move from a higher to a lower energy level, an electron will move from an higher to a lower to a lower. That's when we said it emits a photon or a specific energy frequency. You understand? So if we have to represent it in terms of a graph, we're not going to represent it as a smooth curve. We're going to represent it in a term, something like a ladder, like this. Okay, so that is for quantum physics. So just to make you understand that classical physics will be like, picture yourself like you are sliding down a ramp. So you are occupying every level. You cannot stop anyway. But in quantum physics, picture it like climbing stairs. You can only be at one step at a time. You can never be in between. Okay, so in classical physics, the energy is continuous, while in quantum, we have energy. The physical quantity is quantized, and the energy can only be discrete values, not continuous. Okay, so we can go only from one level to another, not continuous. Okay, so this is an example. Another example can be, for example, the energy of a quantum and quantum harmonic oscillator. So when we talk about an harmonic oscillator, think of what can have an harmonic oscillator. You see, like when you have like a, like you have a spring, look like this. You see? So you have, for example, a spring. So if you basically pull it, you realize that it's going to extend, but it comes back with the same strength. So basically, when we're talking about an harmonic oscillator, we are talking about something that experiences a restoring force, which is proportional to the displacement. You understand? So from an equilibrium position, we can just extend it and then it comes back. So we have examples such as the pendulum. You have that, the pendulum. When you let, for example, a ball here, you hit there, you can see the other one also going and then come back. You see, so it keeps doing this this motion here. So the restoring form can be quantified here, which would be the spring constant multiplied by the distance, the displacement distance from the equilibrium where it was. So we have that. Okay, so this is what we call an harmonic oscillator. So when we're looking at something like an harmonic oscillator, we have when we have to measure the quantum, when we have a quantum harmonic oscillator, in this case now the energy value will just be based on these formulas. So it's not going to be any values, it's going to be quantified at certain levels if the oscillator is harmonic, okay? Which will be different if it's classical, okay? So you have it when you talk about this quantum physics, they are used when we're creating quantum computers, how information are being displayed. Okay, so in terms of the state of motion, so instead of the state of motion, when we talk about the classical, in classical physics, the motion states in the system can be completely determined and predicted. What does it mean? It means that we have the initial condition that is known. For example, if you have this, the ball in the example I gave you in the pendulum there, when you have the ball there in the pendulum, when it's still at rest, we can measure the velocity, like we are at 0. So at equilibrium, which means both the velocity and the displacement can be 0 simultaneously at the same time. So at this point, the total energy will be 0. So the trajectory of it can be easily predictable, when you look at that. So here, it's easy to predict. This is going to go there, comes back there. So very easy to predict that, because that is a classical, in classical physics, in terms of the motion of that. Okay, but in terms of quantum, there is a lot of uncertainty. So we have what we call the uncertainty principle of quantum mechanics. So which means that we cannot determine the precise position and momentum of the system at the same time. So this is how we're going to describe it in quantum. Okay, so in terms of the property, so it is believed that microparticle can be composed of particles. So what does it mean? It means like when we're looking at things like atoms and electrons, those are just considered as tiny solid particles. Those are microparticles. You understand? So when you look at an electron is part of an atom, you understand? So basically they will behave like objects which can be quantified in terms of the position, the momentum at any time. So we can easily find what they do. Okay. But it like an example can be something like the property of sand. So a grain of sand is just a very small particle. You understand? So it's a very small particle. So we can actually quantify it. We can identify it easily. Okay. So, but in quantum mechanics, we say that the particles have both the wave nature, okay, which means wave function superposition and particle nature. What does that mean? So if we look in quantum physics, when we talk about the wave nature, it means that the particles can be represented by wave functions. So we can have the superposition states. In quantum computers, we'll have, for example, a 0 and a 1 at the same time. When we talk about particles nature, particle nature is when we can measure the wave function the wave we say the wave function will collapse to a definite value. So an example can be an electron that can behave like a wave, right? And then we can detect it like that. All right. So in short, what we can say is that in the classical view, particles are just particles, you know. The microparticles are composed of particles. But in quantum, what we can say is particles are both waves and particles. So we're looking at it from a different view there, depending on how you observe them. Okay. Yeah. So looking at, we'll have that. Let me just undo the full screen so it can be in motion. Yeah. Okay, so when we look at it, this is, for example, a classical oscillator where we have a value at each point. So you have the small ball, which is an harmonic oscillator, which is attached to a spring. And as we're moving it, you can see that at each level, the ball can reach every level. But when we talk about quantum physics, we're going to look at an example of a vibration of a diatomic molecule that can be only measured on a quantum harmonic oscillator. So in this case, you see, we can only get certain values. We can't just get any value. So the values are determined. You understand? So we can only go from certain values to certain values. All right, guys. Okay. Okay, so this will be all for today, and we're just gonna complete with this tomorrow. Yeah. Any questions, guys? Any questions? All right. If there's no question, we can call it a day. We can just turn on the camera for the attendance, and then we'll be done.